Oh, hi there, it's Mrs. Bertrand coming to you from the closet, and we are looking at our first set of calculations today. And for the next few lessons, we're going to be looking at how to calculate values at equilibrium, remembering that equilibrium has reactants always exchanging particles with products, which means you will never get 100% products. That is impossible. So we're going to try to figure out how much products we actually do get. If it's not 100%, what is it? So today we're going to be looking at what we call a type 1 calculation, where one value is given at equilibrium. And that's what makes it a type 1. So we're going to do 4 different types altogether with 4 different lessons on different days. And every time it'll be slightly different, but we'll always set things up in the same way. We're going to be creating what's called an ICE table, and the I in the ICE table stands for initial concentration. That means if we do not have concentration values, we will have to get those concentration values. Remember that we have a formula that is C equals N over V, which will sometimes help us. Also, I want to remind you about the unit for concentration. It is moles per liter, but it can also be written as capital M behind the number. You'll see that I use the capital M just as a quick short form oftentimes. The C in the ICE table stands for change in concentration. So what we're going to look at here is how does the reaction change in order to reach equilibrium. So which way is the reaction going to shift? Think about the activity that you did today. We started with 100% reactants, but the reaction shifted towards the product side and to create some amount of reactants and products at the end. And finally, the E stands for equilibrium concentration, which is what we're trying to figure out in the first place. We're going to jump right into a problem, and I'll remind you that when I load the PowerPoint into this program, it doesn't subscript or superscript, so you can do that for yourself. And we're going to do an example so that you can see what it's all about. So consider the following reaction. We have H2 gas plus F2 gas in equilibrium with 2HF. So all 3 ingredients are in the beaker at equilibrium, and we want to know what proportion each one of them is in. If the reaction begins with 1 mole per liter of H2 and F2 and no HF, calculate the concentrations of H2 and F2 at equilibrium if the equilibrium concentration of F2 is measured to be 0.24 moles per liter. The way we're going to start this problem is we need the I part of the ICE table, which remembers the initial concentration of ingredients. So what was put in the container at the beginning. So all we actually need here is just the 1 mole per liter of the H2 and the F2. It's helpful here that they've said there is no HF, but generally speaking, they are not that explicit. Typically in a question, they will tell you what's there and they won't tell you what's not there. It's implied. So if I say that there is H2 and F2 and I don't say anything about HF, it means there isn't any. This is how we set up an ICE table. So we write the equilibrium equation along the top, and then down the left-hand side we write ICE, and then we start following the information. And again, the only thing we need to know is what is in the initial part of the ICE table, which we get from the word problem. And we already were given that information, so I'm going to go ahead and put that in. We know that there was 1 mole per liter of H2 initially, and 1 mole per liter of F2 initially, and there was no HF. So that's the only thing I actually need to get from the problem. Even though there was another piece of information, I don't need that yet, because from here I can actually solve the rest of this table. So the second part of the ICE table is the change in concentration. So what has to happen in order to reach equilibrium? For a question where there is a 0 anywhere in the table, left of the arrows or right of the arrows, doesn't matter, the 0 helps us figure out the C. The C change means how do I make equilibrium form? Well, I can't have 0 of anything at equilibrium. Equilibrium, remember, is always a mixture of some proportion of reactants and products. So if I have a 0, it means this reaction has to shift towards that 0. I have to create some products. It's impossible to have an equilibrium without any. So that means the shift will go from the reactant side to the product side. It will shift to the left to create equilibrium. So the left-hand side, the reactants, we're going to subtract some reactants here because they're going to get smaller. We're going to use some of them up to make some products. So the products will get bigger. We're going to use a plus sign. Now we don't know exactly how much is going to shift, but we do know the proportion. So we're going to use an X to represent how much, and the proportion is according to the balanced equation. So they react in a 1 mole to 1 mole to 2 mole relationship, and so we use the coefficients in front of the X's to figure out the proportion of change. The last part of the ice table is the equilibrium, and E is actually I plus C just added together. So if I do 1 minus X, that's the H column. 1 minus X is the F column, and 0 plus 2X gives us 2X, that's the HF column. So I just do I plus C makes E. Now it's time to go back to the word problem where they gave me an additional piece of the puzzle. They actually told me that F2 at equilibrium is equal to 0.24 moles per liter. Equilibrium for F2 is also 1 minus X, as I can see from my ice table, which means I can let these two things be equal to one another. So 1.00 minus X is F2 at equilibrium according to the table, and 0.24 moles per liter is F2 at equilibrium according to the question, which means I now have a way to solve for X. So I'm going to rearrange, and I'm going to solve. Now that I know X, that's great because my whole goal is to figure out what the actual values of everything are at equilibrium. So this, now that I know what X is, I can substitute it back in and solve. So I just did F2. It was given. H2 is 1.00 minus X. X was figured out to be 0.76. So we've got 0.24 moles per liter, which makes sense because H2 and F2 should be equal. They're both 1 minus X. And then my HF is 2X. I'm going to bring this calculation down to 2 significant digits here, so 1.5 moles per liter. So let's just review our steps for solving this type of question. Number 1, set up an ice table. Number 2, put in your I. These are always given. These are your initial concentrations. They're going to come right out of the word problem. Number 3 is the C, the shift towards the 0. So you're going to put in pluses and minuses of X and use the coefficients to figure out how many X's. In part 4, that's your E. You're going to add your I and C together. In number 5, you're going to let the entity at equilibrium equal the same value in the equilibrium part of the table and solve for X. And finally, 6, you're going to solve for all other entities at equilibrium, which is our goal. What we're going to consider now is how do we represent the value that we got at equilibrium as a percentage? So how can we determine how much product there was at equilibrium? We figured out what it is in moles per liter. How do I convert it into a percentage? So if I want to know at equilibrium what percentage in the container is actually products, how do I do that? So this is going to be a comparison of how much product we actually got, which we just figured out, versus how much product we should be able to get if I had a one-way arrow. This means we're going to use some stoichiometry. It's been a while since we've done some stoichiometry, so let's review. When we're trying to figure out percent of product, again, this is going to be focusing on the HF. What we need is we need to go back to the I part of the ice table only. It doesn't matter the rest of the stuff that we did at this point, we just need the I. We're going to do a little bit of stoichiometry so that we can compare it to what we actually got. So what we have is 1 mole per liter of H2, 1 mole per liter of F2, and these are in a 1 to 1 to 2 relationship. And stoichiometry is just about a mole ratio using coefficients. So if I have 1 mole per liter and 1 mole per liter, I should be able to make 2 moles per liter. So I'm just following a ratio. If the numbers were trickier, I could set it up in a more defined fashion. So for instance, if I want to know the concentration of HF using the concentration of, let's say, the H2. Since the values are the same, it doesn't matter, so I'm going to use the H2 here. I can set up a mole ratio. Hopefully you'll remember this vaguely from grade 11. We put HF on top with its coefficient, so there are 2 HFs for every 1 H2, and so we're just doubling our value to get our value of HF. So same thing, a lot of times with this math you'll notice that it's pretty straightforward, the numbers are easy to work with, but if they're difficult we can put it more formally like this. So now what we're going to do is we're going to compare the value that we should be able to get with the value of HF we actually got at equilibrium to figure out what its percentage is. We call this a percent reaction, and we'll formalize it a little bit more in a moment. So we got 1.5 moles per liter, but according to our math, we should have been able to get 2 moles per liter if this reaction would have gone to completion, if it was a one-way arrow. So what we can do is we can divide it out, and we get 75%. What this means is that 75% of what's in the container is products at equilibrium, and only 25% is reactants. That's pretty good if you're trying to get products. Most of it, 3/4 of it, is product. Sometimes this is written above the arrow as a way of showing how much of the reaction ends up in the product side. So let's do that whole part a little more formally. So this is called a percent reaction. It's a comparison of how much product you should make if 100% of product is made, so that's the stoichiometry piece, versus how much you actually make when equilibrium is reached, which is the first part that we did today. And it's always in terms of products. We could look at it in terms of reactants, but we never do, because remember, if you're in a company and you're making something, you're trying to make products for your customer. So this is what our equation looks like. The very top is the actual product yield. So again, this is the product at equilibrium. So this is going to be using our ICE table. And then at the bottom is the theoretical product yield. And this is the concentration of product using stoichiometry. So for this part, we're going to go back to the I part of the ICE table. That's the only part we need to figure out this bit, even though we have lots of other things to distract us. Let's try this problem on for size. The concentration of N2 at equilibrium was found to be 0.25 moles per liter. If 0.65 moles per liter of NH3 was placed in the container originally, what is the percent reaction? So we're just practicing that percent reaction piece at this stage. So we need to figure out what concentration of products we could make here, knowing that we have 0.65 moles per liter initially in our container. So I've just set up the problem here just with the I part showing. So what I want to know is the concentration of products. Now, I have 2 products. When I'm doing this percent calculation, I can look at either of the products, but I'm going to choose the one that's got the easiest ratio. I'll show it to you both ways just so you can see that it doesn't make a difference, but I would go with the easiest ratio, which is the N2 here, because then I can just do the math in my head, or I can do it really quickly. So I want to know the concentration of N2, and they're in a 2-to-1 relationship with each other. So that means for every 2 NH3s, I only have 1 N2. That means all I'm going to do here for the 0.65 is I just have to divide it by 2, which gives us about 0.33. Now I can also do that more formally. I showed you how to do that with mole ratios. Let's do that as well. So the concentration of N2 is what I'm looking for. I'm using the concentration of the NH3. I'm dividing by, or multiplying rather, by my conversion factor. So I have 1 N2 for every 2 NH3s. Notice NH3 has to go on the bottom here. That's why I know that's going to be divided. So again, I get this value here. Okay? So let's set up our percent reaction then. And for my percent reaction, again, I have to go back to that value that was given at equilibrium. They told me that at equilibrium I have 0.25 moles per liter of N2. That's how much I actually got at equilibrium. According to the stoich, I should be able to get 0.33 moles per liter if it was 100% reactions. And that leaves me with 77%, which again is pretty good if I'm trying to make product for my customer. I'm getting obviously more than half of what I should be. Okay, so that's how we do a percent reaction. Let's put it all together in another example. So this is example number 2. There's a couple of things that are a little bit different here. So again, we have our equilibrium reaction. It's the same one we just saw as an example for just doing percent reaction. This one tells us that when 4 moles of NH3 is introduced into a 2-liter rigid container and heated, the amount of ammonia changes as shown in the figure below. We want to determine the equilibrium concentrations of the other 2 entities. So we have a graph. It's showing us an amount in moles on the y-axis over time, and we're going to solve for the values at equilibrium. So we're going right back to the first part of our lesson where we're figuring out values at equilibrium. So we're going to be starting with that ice table, and then we'll go back to part B where we do a percent reaction afterwards. So I've set up my ice table. My balanced equation is along the top. My ICE is down the left-hand side. I'm going to go back to the word problem, and I'm going to figure out what's initially in the container. So this one's a little bit different than the last one because it was given to me as moles and volume of container. So the concentration that was given is the NH3, and we were given to it as 4 moles in a 2-liter container. So again, I'm going to convert this into a concentration before I put into my ice table, because remember that I stands for initial concentration, not initial moles. So let's put it in 2.0. I'm going to use my capital M there. It doesn't say that there is anything else in the container, so by excluding the other materials, we can go ahead and put zeros in there. Once again, because there are zeros in the ice table, I know that I have to shift the ingredients to the right-hand side. Reactants have to turn into some amount of products, because at equilibrium, just like when we did that activity today, or yesterday rather, you have a certain amount of both reactants and products in the container at the same time when you reach equilibrium. So that means the left side is the minus side, the right side is the positive side. It's going to get bigger. This is almost always the way it shifts, but not always. We'll see some variation as we go from one problem to another. But if there's a 0 somewhere, it always shifts towards the 0. So if there was a 0 for the reactants, we would shift to the left. So the proportion of how they shift, remember, is according to the coefficients. So we have a 2x, an x, and a 3x. And lastly, our equilibrium is I plus C added up. So 2 minus 2x, x, and 3x. All right, this problem is a little bit different in terms of how we solve it because they gave us a graph. I've just done a little sketch of the graph over to the side here. And again, this is a graph that is showing us the concentration of NH3 when equilibrium is reached. And we know from our activity yesterday that equilibrium is on a graph when it goes horizontal. So if we have a look horizontally, this is 2 moles. But again, remember that when we use our ice table, everything is in concentration. So it's 2 moles at equilibrium. The container is still 2 liters. So we actually have a concentration at equilibrium of 1 mole per liter. So I'm going to put this up here because the concentration of NH3 at equilibrium is 1 mole per liter, and the concentration of NH3 at equilibrium according to the table is 2 minus 2x. So both of these things are the same. They're both referring to the same moment in time, NH3 at equilibrium. That means I can let them equal one another. So 2 minus 2x equals 1.0 mole per liter. Let me put that per liter there. There we go. And again, you can use the big X or big M for that as well. So let's rearrange and solve. X should be 0.50 moles per liter. And now that we have X, we can go back and we can solve for values at equilibrium for the other 2 entities. So N2, nice and easy, it's just X, so it's going to be 0.50 moles per liter. And the H2 is 3X, which is going to be 1.5 moles per liter. We're now going to tackle part B of that question, which is looking at percent reaction. So again, we have two pieces of the puzzle that we need to solve for percent reaction. We need the value of product at equilibrium, and we need the value of product versus at stoichiometry, so at 100%. So again, I'm going to start by going to that stoichiometry piece. So all I need is the I part of the ICE table, so you'll notice that I didn't bring anything else with me. And what I'm trying to figure out is what's the concentration of the products. So once again, I actually only need to know one value here, and because I know both values at equilibrium, I brought those with me, I could actually use either one of these to solve for percent reaction. So I'm going to show you both just so I can prove that to you, but again, I'm going to start with the easy one, because if I was going to do it, I would only do it once anyways, and I would choose the easy value here. So remember that percent reaction is the value at equilibrium. So working with N2, the value at equilibrium was 0.5, and then it's divided by the value that we should be able to get based on stoich, a one-way arrow. So for every 2 NH3, we only get 1 N2. So if I have 2 moles per liter, I only get 1 mole per liter here. So this is my situation times 100%, and that's going to be a 50% yield. So if this is what I was making for my customer, this would not be great. Every time I did this reaction, only half of what I get is actually product. So not very good. Let's consider the second ingredient here, just so I can show you that it doesn't matter which one you choose. Percent reaction is only one value for the whole reaction. Let's do this one in blue. So percent reaction, this time we're going to do it in terms of the H2. So the H2 is 1.5 moles per liter. This is where the stoich's a little bit trickier. It's a 2 to 3 relationship. Because the numbers aren't quite as nice, let's do a more formal mole ratio down here at the bottom. So if I wanted to know the concentration of the H2 using the concentration of the NH3, I would set up what am I looking for equals what do I know, and then I'm multiplying by that conversion factor, which is the coefficients. So the 3 H2s go on top. I'm looking for H2. The 2 NH3s goes on the bottom, since that's what I want to get rid of here. And so the value that I should be able to is 3 moles per liter. And again, I'm going to bring that up to the equation here and finish it off. And once again, I get 50%, which isn't surprising because the equilibrium is just one container, so it has only one percentage. So it doesn't really matter which product I choose to look at, but again, if this was me, I would always go with the easier version. This is the homework that you're going to try, and once again, you can reach out by email if you have some questions, and I'm happy to talk to you, and there will be a homework sheet posted as well to request take-ups.